Hello. All right, Chapter 17, Applications of Thermodynamics. And there's my teacher for today, a little frustrated. I'm a little frustrated. Things keep changing. AP Central keeps changing, and then some of the guidelines from our own district keep changing. But I'm going to keep moving forward as best I can under those restrictions and do what's best, at least in terms of integrity, and do the best we can in order to do well. But anyway, chapter 17. Let's see what we got. All right, so chapter 17 focuses on two things. First of all, will a reaction occur under a certain set of circumstances without us having to add any energy? That's what they mean by spontaneity of a reaction. And in terms of that spontaneity, there are a couple of thermodynamic principles involved, and that includes enthalpy, which is delta H, and we already did enthalpy, and they assume that you remember it. Um, that's. So, in other words, the calculations for delta H are the same. You do the whole summation of the products minus summation of the reactants, but now they're going to throw in entropy, which is randomness, and then the whole thing together. When we consider the whole thermodynamic environment, we call that Gibbs free energy. So Gibbs free energy is really this involves the second and first law of thermodynamics, that we're still talking about energy, and that energy is providing the driving force for reactions. So it is still Q plus W, which is what this kind of looks like, except for that here, this is really our W. Taking a look at randomness and how pressure and volume affect work energy. But it's also an application of what they call the second law of thermodynamics, which is it's not just about the energy of the reactants and the products, but it's also about states of randomness. In other words, the universe is tending towards more and more entropy, which means that things are becoming more random and scattered throughout the universe. So there is also a chemical tendency towards this, which involves motion and different types of bond rotations and compressions and that sort of thing we'll get into in detail. Okay, first of all, examples of spontaneous reactions. Again, things that occur under normal atmospheric pressures and temperatures. The burning of methane. Now, we know in order to get that reaction to start, you have to activate it. You have to provide the activation energy. But once you do that, it feeds off of its own energy. It is delta H negative. And it has a driving force, two driving forces here. One is the production of carbon dioxide, small covalent molecule, and the second, the production of water molecules on our planet. The second example is just melting at 25 degrees C. Now notice that this is temperature dependent. Spontaneity depends upon where you are in the universe, so it depends upon your thermodynamic environment. In this case, we have 25 degrees C, which is above the normal melting point for water. So we have enough thermal energy for this to occur without us having to do anything about it. All right, so what affects spontaneity? First of all, when you're dealing with delta H, we said that the nature of the universe is towards stability. So delta H negative values in kilojoules per mole reaction, those things tend to be spontaneous under normal conditions. They're not all spontaneous. Again, this is just a guideline. There are many exceptions to that. But this makes sense because we're taking high energy reactants and we're turning them into lower energy products. So it makes sense that this follows our thermodynamic principles. Second, is the system moving towards a more random state? In other words, more freedom of degrees of motion. Not always is that a spontaneous reaction because the energy factor is much larger than the randomness factor, and that's something to consider. So if you look at delta H values, again, delta H values are normally in kilojoules per mole reaction. However, delta S values, the entropy values, the randomness, are measured in joules per mole reaction. And there's generally an increase in this as a guideline throughout the universe, so these tend to be positive values, but much smaller in terms of the units because the randomness factor is much smaller than the energy factor. So in terms of entroscopic view of the universe, they say that the nature tends towards disorder. But remember, they're talking about the entire universe here, and we're talking about small systems. So there are certainly many examples where we have a reaction that's spontaneous, but yet we're creating something that is more ordered. For instance, double displacement reactions. In a double displacement reaction, you're producing a precipitate. A precipitate is certainly more ordered than the loose, free-flowing cations and anions that make up a dissolved particle. Entropy, so they're going to use the term delta S, and we're going to do all the same calculations for delta S that we did for delta H. So for delta S, we're looking at the entropy of the products, and we're subtracting out the entropy of the reactants. In other words, we're comparing the two. So this is a state function. As solids go to liquids, you increase the free range of particle motion. Liquids can flow where solids can't. Solid particles are locked into position in their crystal lattice, whereas in a liquid, the particles are separated enough to allow them to slide one over top of the other. So as you melt something, you are increasing the entropy. You're increasing the particle motion. So we would say that delta S for this is positive. In terms of gas reactions, this is not true for liquids and solids, but it's definitely true for gases, that when you increase the number of particles, since gases have free particle motion anyway, the more particles you have, the more degrees of freedom of motion or more randomness of motion you have. So more overall motion. So if you're creating products which have a larger number of moles of gas and reactants, you've increased the number of particles that have free random motion, therefore you've increased the randomness of those particles. Determine if the entropy of the following reactions will be positive or negative. All right, so in this one we have a gas reaction, and we are dealing with 2 moles of sulfur trioxide, but we're creating 3 moles of product. So again, we're going from 2 moles of gas to 3 moles of gas. So this is an increase, and we would say that delta S here is some sort of positive value. Let's get rid of all of that. Here you're going from 4 moles down to 2 moles. So you've decreased the number of particles that have free random motion. Therefore, you've decreased the entropy. Our delta S value would be some sort of negative value. Again, in kilojoules or in joules per mole reaction. Yay, got it right. All right, so delta S naught calculations, the same way you did delta H, they'll give you a list of values based upon standard state. Now, the standard state here is 1 atmosphere. It's also listed as 25 degrees C. But on the AP exam, if you decide to use 0 degrees C, if they don't specify a temperature, they'll also allow it. The truth of the matter is delta H and delta S is not very temperature dependent, so at least under their standard states. So therefore, it really doesn't matter what temperature you choose. So really what you have to focus on is that if we're dealing with delta S naught or delta H naught, then we're dealing with some sort of standardized pressure, in this case 1 atmosphere. Delta S is positive for elements and compounds. That's different than delta H, because when we were dealing with elements or the H plus ion for delta H, we said that the value was equal to 0. But with delta S, there is some randomness. Even in things that are in crystal lattices, there is some degree of freedom of motion there. So therefore, elements actually have an entroscopic value. So when you look at a table of values, again, the delta H values are going to be in kilojoules per mole, and the delta S values are only in joules per mole and joules per mole Kelvin. Again, the delta H factor numerically is a lot more significant than the delta S factor, but the delta S factor does play a part. Now, notice there's a unit for temperature, right? We have Kelvin. So that means that as we change the temperature, this entropy value plays a bigger role. And that makes sense because if we increase the temperature, things melt or they boil and their degrees of freedom of motion change, or bonds break if we add enough thermal energy. And if we remove thermal energy, then we have the opposite happening. Things are becoming more ordered. They're liquefying or they are freezing. Reactions with delta S as positive tend to be spontaneous at high temperatures. Okay, well, that makes sense also because we said that things that are endothermic, for instance, benefit from higher temperatures. Well, we could say that about entropy also. Things that are entroscopic, where the entropy, the randomness is increasing, also benefit from high temperatures. As the temperature goes up, the degree of freedom of motion goes up. All right, so here's some examples, and we already did melting. As we go melting, we're allowing flow, freedom of motion of the particles slide over top of each other, so we're increasing the randomness. For liquid water becoming a gas, we're boiling, so we're going from flow to free random motion. And for the last one, this would be the smelting of iron. So we take iron oxide from some sort of rock, and we are going to coke it by heating it through hydrogen gas, and that's going to create iron and 3 moles of water. Now, how would you know that that's delta H, the delta S positive? Because you have 3 moles of gas on the reactant side, and you have 3 moles of gas on the product side, so the moles are equal. But the difference is, when you have a hydrogen molecule, you have a hydrogen and a sigma bond connected to the other hydrogen. So you get tumbling, you get rotations, you get those sort of motions in terms of bond rotations. But with water, you have 2 sigma bonds. And in a sigma bond, the bond can rotate completely in 360 degrees. So you wind up with more bond rotations in a water molecule. Therefore, you have more randomness, more degrees of freedom of motion. All these reactions are endothermic, but become spontaneous at high temperatures. Again, that makes sense because an increase in heat favors the endothermic process. Okay, so in an energy exchange, we can look at the first and second law of thermodynamics. And the first law is our delta H, or enthalpy. Energy cannot be created nor destroyed, just transferred from one form to another in and out of a system. And the second law of thermodynamics, the difference is that we're actually losing some heat energy for every time we have a particle collision, and that heat is being converted into work. So if we're increasing the work energy, then we are increasing the amount of randomness. So here's an example of a structure. If we increase the space between the particles, now the particles can slide over top of each other, and we are increasing the randomness. So delta S here would be positive. We said there are all types of bond motions. To understand, with a double bond, you have a pi bond. So you don't get free rotation of the bond, but you do get all of this bending and stretching. Again, it's best to think of a bond not as a wooden stick like in our models, but to think of them as springs, where they can be stretched and compressed. So even in a double bonded substance or a triple bonded substance where you have pi bonds, there still is random motion. So the more bonds you have, the more entropy you have. In a single bond, not only do we get 360-degree bond rotation around the axis, but we do also get that stretching and compressing of the bonds, and we get what's called scissoring and rocking, where the particles can actually move towards each other or in the same direction away from the other two, in this example, the other two that make up the tetrahedral substance. the other two atoms. In terms of 360-degree bond rotations, if you take something like this, let's say that this is a carbon and this is a carbon, and then we have 3 hydrogens. So we're dealing with ethane. If we were to rotate this, we can rotate these bonds, these 3 hydrogens connected to the carbon along this sigma bond, we can rotate it up to 360 degrees. As we rotate it, if we put it into what's called an eclipsing arrangement, then the hydrogens that are connected to the blue and the red here, if they line up one behind the other, then those charge clouds interact with each other and it creates repulsion, and that creates high energy. Whereas if you were to continue to rotate this bond another 60 degrees, you create what's called a staggered relationship, and then the charge clouds on the hydrogens no longer interact with each other, and that gives you a low energy state. So as you rotate 360 degrees around a bond, you are changing the amount of internal energy, because as you rotate, things are either lining up in an eclipsing arrangement, or they're lining up in a staggered arrangement, and those interactions among those charge clouds changes the internal energy. So we do, again, have entropy here. We have a lot of different of what's called rotamers, where you have the same molecule, but because of how it's rotating around the bond axis, you actually get different energies. If you have isomers, for instance, let's say we have 6 different isomers, and we're going to create, I don't know, let's create a hydrogen molecule. Well, that's a bad example because hydrogen only has 3 isomers. So we'll just call this X. So we create diatomic X, X bonded to X. And let's say atom X has 6 different isomers. Well, there's actually 36 different combinations for those isomers that you can get. And so in terms of entropy, now you have different masses that you can get, where you're taking certain isomers and bringing them together to make that molecule. So it's like a lot like dice, where if you have different possibilities, then you have different numbers of permutations, and you wind up with a randomness of results. But that randomness of results still resembles a Gaussian curve, where we have, for instance, the masses. If you have a high mass isotope like isotope 6 and a low mass isotope like isotope 1, and you get in sort of an average mass between them. So there are a lot of ways to come up with an average mass substance in terms of isotopes, where there are very few isotopes that are created with an extremely low total mass, and isotopes that make up this diatomic molecule where you have an extremely high mass. If we have 3 molecules, then we increase the possibilities. If we, 3 atoms making up the molecule, we increase the possibilities. Again, this is on the pretense that we have 6 different isomers for each of those atoms, but bringing them together, we now have a total of 11 different possibilities that we can get. That's for 2, this for 3. For 3, we wind up with 16 different possibilities, but 216 different microstates. So again, by increasing the number of atoms in the molecule, we're increasing the randomness because of the possibility of isotopes. I'm going to stop here and continue on the next video.